All right, so what we have left to do is prove this claim, and then we'll be done with our calculation of the area of a 2/3 ideal triangle. And what I'm going to do is I'm going to draw the picture from the book, which in my copy is in page 94. And really, the exercise we're doing right now is this is problem 7.2c, if you want to follow along in the book. But the picture I'm going to create, I need to prove this claim, right? And so somehow I'm going to have a picture that involves three different 2/3 ideal triangles. And the three are going to be the ones with exterior angle alpha. That's, the area of that's going to be this one. Beta, and then I need another 2/3 ideal triangle with exterior angle alpha plus beta. So I need a picture which has all those triangles, and hopefully I can use that picture to show that these areas on the left and right side of the equality are equal to each other. And they helpfully give us the picture in the book. So I'm drawing this picture not on the upper half plane model. I'm just drawing actual hyperbolic triangles. And it looks like this. So see if I can copy it kind of accurately. So let's let this angle be alpha. If that's alpha, then that's the exterior angle of this 2/3 ideal triangle right here. And so this area here is going to be a row of alpha, right? And now I also want a 2/3 ideal triangle with exterior angle beta. I can do that on the other side. So if this angle is beta, they're not meant to be congruent. Maybe I can change that. Something like that. So alpha and beta are not equal. I don't want them to look that way in the picture. But if I have this exterior angle beta, then there's another 2/3 ideal triangle I can form with exterior angle beta. That's this triangle here. Okay, and then finally I need an exterior angle of alpha plus beta. Well, that angle's right here. This is alpha plus beta. And so the corresponding 2/3 ideal triangle with that as its exterior angle is right here. It's this triangle here. Notice that has exterior angle alpha plus beta. And that's the picture they give us in the book to kind of help us start this problem. So what I'm going to start by doing is kind of labeling everything in sight. Just to match the book's notation, they call this vertex A. They call this vertex P. And let's remind ourselves what the 2/3 ideal triangles we're looking at are. So the first one is this blue one. This has exterior angle alpha, and so the blue area is a row of alpha. And then we've got, maybe I'll make it purple. This has exterior angle beta. This is a row of beta. And then there's the alpha plus beta, which is this part in here. Okay, and so we want to show that the blue plus the purple is equal to the red. Notice there's a little bit of overlap between the purple and the red, so let's give that region a name. This green region might be called a 1/3 ideal triangle because it has two actual vertices and one sort of asymptotic vertex off to the right. I'll call this area J. So let's let J equal the area of the green part. Okay, so another way to say it is it's the overlap of the red and the purple. While we're labeling things, we might as well notice that there's an extra 2/3 ideal triangle here. So if I call this angle gamma, this is the, choosing a color, this is the exterior angle for another 2/3 ideal triangle, this one right here. So that's a rho of gamma. But actually, it's also the exterior angle for the, the opposite 2/3 ideal triangle. Which is this one here. So this is also a rho of gamma. And since we know that any two-thirds ideal triangles with the same exterior angle are congruent, we know that this area is equal to that area. Those are the same size. And so with all these pieces, we should be able to prove the claim now. So the left-hand side of the claim is the area of alpha plus area of, or the area of the 2/3 ideal triangle alpha plus that of beta. So it's blue plus purple. So we got a rho of alpha plus a rho of beta. Now just looking at the region enclosed by blue and purple, it's this part. There's another way of writing that. I could write it as the green plus this a rho of gamma on the left side. So just by looking at this picture, I see that that's equal to J plus this 2/3 ideal triangle gamma, just because they take up the same area. But then I've got two copies of the 2/3 ideal triangle with exterior angle gamma. The other was the orange one on the right. And so this is equal to, I could just as easily write J plus this a rho of gamma. They're the same number because it's the same area. These are equal to each other. And so what I have here is now the green plus the area of the orange, but you can see that that's exactly the same region as is given by the 2/3 ideal triangle in red with exterior angle alpha plus beta. And so this is equal to a rho of alpha plus beta. Okay, and that's the proof. It's kind of a complicated diagram, so it's helpful that I have all these colors at my disposal. And this shows that they're equal. And let me add that the next step is to show that if you have a continuous function which satisfies this claim, which we just proved, then it must be linear. And I'm leaving that as an exercise to you. One final exercise, which is a good way to test your understanding of this, would be to try to repeat this proof, but instead of just drawing these asymptotic triangles in the hyperbolic plane, use our upper half plane model. So using the upper half plane, draw this same picture. So draw the same picture on the upper half plane. Where we know what the geodesics look like. So with geodesics, given by half circles and vertical lines. So this picture here, we drew it kind of as if we were drawing triangles on the hyperbolic plane itself. On the other hand, we've worked a lot with this upper half plane map of hyperbolic space, and so you should be able to draw this picture, but using what we know to be the geodesics on this upper half plane map, which are the half circles and vertical lines. So see if you can draw basically the image of this picture on the upper half plane and try to reprove the theorem using the exact same arguments, but using the picture on the upper half plane. All right.